Oh, thank you very much, Mr. Chairman, for the introduction. I'm going to be looking at stress in bipolar devices. There's a lot of stress induced during the fabrication and packaging of bipolar integrated circuits, and this modifies the parameters of the devices and ultimately changes the current gain, and that will change parameters in the various circuits. The offset voltage shifts are recorded, band gap reference voltage changes, thermometry errors in thermometers. So we want to come up with a comprehensive understanding of what's going on and a good model for the stress dependence in bipolar transistors, be able to simulate what's happening in circuits, as well as try to come up with strategies for minimizing and or mitigating the impact of the stress on these precision analog devices. Interestingly enough, we've made measurements on many transistors, and the stress dependence from a circuit point of view and a device point of view is really macroscopic. So we've picked a very simple bipolar device model. It's a three parameter model called the transport model, which is a form of charge control model. The collector current, and the base current are of this form, with saturation current and early voltage and current gain being the only parameters in the model. And of course, temperature is a key thing as well. So we'll look at that model. We're interested in the behavior of the collector current, which is flowing upward in the device. So we'll explore these parameters in some detail. A couple of them very quickly, actually. Saturation current is the one thing that's really characterized well in the literature. It's characterized by a set of piezo junction coefficients that talk about the variation of the minority carrier conductivity in the device, which is a product of mobility and intrinsic carrier concentration squared and a few other parameters. If we look at the fractional change in that, you get the fractional change in mobility and the fractional change in Ni squared. We'll talk about the mobility more as we go. These are our plots of simulations using the Beer and Picus deformation potential theory along with first principle solid state theory to generate what appears to be an excellent prediction of what the variation of Ni squared is. And it characterizes very well these piezo junction coefficients. So that's pretty much something that we can rely on in the literature, so I'm not going to explore that any further. Similarly, with the early voltage, we've gone back and measured that on transistors using a technique we developed probably 20 years ago now to extract the early voltage from the open circuit voltage gain of the transistor. And this is one set of measurements. If you fit a curve to that, it's essentially constant. If you go into the theory of the device over here, and I'm not going to dwell on that, really the early voltage is has a geometrical dependence, and one would actually expect it to be stress independent. It characterizes how the collector current and in some cases the base current vary as you vary the collector emitter voltage on the device. So it's not going to vary. Indeed, if it varies a little bit, it really doesn't affect other measurements in the device. So we don't have to worry about that. The main one is the behavior of the current gain, trying to model what's happening in the current gain. So here we have a little block model of the transistor with the collector current going upward in the device. And the current gain is the ratio of the collector current to the base current. As the carriers flow across the base, some are lost to recombination between electrons and holes, and that's the recombination component of base current. And from that we can define a transport beta, transport current gain, transport limited current gain, and it's dependent primarily on the mobility here in the base. And the second component is due to back injection of carriers into the emitter, which reduces the emitter efficiency below 1, and so we can define a emitter efficiency limited current gain. If we go through the device physics, we end up with the difference in the mobilities in the base and emitter, and the difference in the intrinsic carrier concentration squared. if we look at the overall current gain, then we can combine those with the fraction delta, and delta is the fraction of the current gain that's determined by back injection, or a fraction of the base current that's due to back injection, either way. One key issue here is that these mobilities are all minority carrier mobilities, and for a long time there were not good data on the minority carrier mobilities, but I think it's become pretty much a solved problem. This graph gives you the mobility versus the impurity concentration in the structure, and the upper two curves are for minority and majority carrier electrons, and the bottom two are for holes. And they're very, very similar until you get out to very heavy dopings, but out there these coefficients are getting small enough that it doesn't matter much. So we're assuming that the piezoresistive response, the change in mobility basically, is the same for majority and minority carrier electrons. The piezoresistive coefficients are different on the 100 plane and the 111 plane, the two planes that are used commonly to fabricate bipolar circuits. Most of the bulk today is on the 100 surface, and we use the pi coefficients, pi ij. There are three of them, pi 11, pi 12, and pi 44. And on the 111 surface, we use the B's just because they appear in combinations all the time, and they're down here. But they're just linear combinations of the pi's. And what we've done is go through the literature and look at the data and try to pick out the values that correspond to the base and emitter regions of the bipolar transistors. So these are all here for reference. A lot of these equations are here for reference, so if you pull down the slides and read the paper, you can dig into it and figure out what's going on. So if we go into the 100 surface, we're interested in the mobility now in the vertical direction in the transistor, changes in mobility induced by in-plane stresses as well as the out-of-plane normal stress. So it's pi 11 and pi 12 that enter into these expressions for the current gains. And we have the mobility variations here, and again, Ni squared in the beta gamma, and in the beta T prime, it's just mobility. So that's a big difference here if there's any band gap narrowing. There's another function, there's another thing that's very important. We can expect the temperature coefficient of the injection limited beta to be positive and potentially very large if there's band gap narrowing, whereas that associated with the transport limited beta will be negative and relatively small. So that helps us differentiate these if we need to. So here's the typical plot on the 100 surface, PNP transistor on the top. And you see it has very small slope here near the origin. And then there's some curvature, or you can really fit a straight line to that. And the NPN has a much higher slope. If we look at the PNP equations now with the numbers in them, look at the two components of beta, we see that the transport limited one has a very small slope and no curvature, and the back injection has a larger slope but can have curvature. And it looks like it could be consistent to either one depending on exactly which coefficient you pick. So we've gone through and measured the temperature coefficient, and it's consistent with band gap narrowing at about 22 millielectron volts. And we've also measured the change in base current with collector emitter voltage, and that shows variation that gives a delta of 86%. So 86% of the base current's from back injection, and about 14% is from transport loss. Another thing that could be done with stress here, by the way, is there's a 10-to-1 difference here, clearly in the response to sigma 3,3, which is much more difficult to apply, but we're looking into that. So that one is, the PNP is described by a combination of these two terms. If we look at the NPN, it's a nice straight line. You do see a minor curvature if you go out a little bit farther. And so that looks like it's described by the back injection. And you can see the slope here very well matches the slope in the NPN. This one also does, but there's no curvature. And if we go and measure the temperature dependence to the current gain and the voltage dependence to the base current, it confirms that this is 100% back injection. And these are just quick pictures of what's going on there. If you look at the fractional change in collector current, you see a large change with the collector emitter voltage here, which you'd expect. But the base emitter voltage doesn't change at all, essentially no change. And that's indicative of a back injection case. And here's the beta characteristics there versus reciprocal temperature, and that's the exponential dependence, and that has it's a 17 millivolt band gap narrowing term. Here's what you get for the PNP. This is the collector current variation now versus collector emitter voltage, and this is the base current variation. And that signature indicates that there's back injection. Transport loss. If this slope were equal to that slope, it would be 100% transport limited current gain. But this indicates there's a 6-to-1 ratio between the forward and between the transport loss and the back injection loss. Do the same thing on the 111 surface, and here's what you get for an interesting case. This is just an NPN. It's a structure we had around that was a Van der Plas structure. It was meant for a Van der Plas test, but it can also be operated as a vertical NPN transistor. And we operated it in two different modes. The other transistors were sub-quarter micron based devices. This is a big fat based device, at least 3 microns. And if we look at the normal mode, which is this curve, it has a very shallow slope of about 50 reciprocal terapascals, and that no curvature, and that fits the transport limited model as one might expect for a 3 micron wide device. The recombination current goes as the square of the base width, so this ought to have at least 10 times the recombination current of the previous one. If we turn the transistor upside down and operate it in inverted mode, then we expect to have a huge back injection current, and that ought to correspond to this equation, and it does. The slope here is the initial slope is easily modeled by the piezoresistive equivalent coefficient, and then we're getting curvature that we can predict from those Ni squared curves. So one of those is transport limited, and one of those is back injection limited. We haven't had time yet to check those by measuring the temperature coefficient. And you can take that data, similar data, and plug it into the SPICE simulation. This just shows the simulation of a simple little op-amp circuit where we're varying the current gain of the PNP transistors, and you can easily get a variation in the offset voltage, and it very well matches what you predict from circuit theory. So we've modeled the stress dependence of both the early voltage and the current gain. Early voltage is essentially independent of stress. The NPN current gain variations with stress are modeled very well with the first order behavior, and you can include some second order behavior from Ni squared. Actually, the PNP current gains don't very much vary with stress, but this is not true of the currents, which I didn't show. Both IB and IC vary almost identically, and that's why the current gain doesn't vary much. Curvature is consistently observed in the PNPs, but not in the NPNs, but that's in the range of stress where we are. It's being really masked by the mobility change within the NPNs. And stress can, in certain cases, be used to differentiate the modes of current gain in the bipolar devices. So we think we're well on our way to being able to model these things and predict what's going on. Thank you.